Hello, my name is Lorena Rambu and I'm in Physics 2211, section M01, and welcome to Physics is Fun! In today's episode, we will be tackling the world's largest rope swing problem. So in order to visualize the forces, we're going to draw a free body diagram. So we're going to have the person is going to be the dot right here, and the two forces acting at this instant are gravity, and it's pointing down. So we have negative mg, and then we have the normal force or the tension force from the rope, and that we're going to list as T1. So after we got the information we got from our free body diagram will be used for Fnet. So we have Fnet is equal to negative mg. And then we're going to use the momentum principle. So we have delta P is equal to F net delta T. And what we're going to do next is we're going to keep on working this out and simplify it. So we're going to have PF minus P initial is equal to F net delta T. And then because P initial is 0 because the velocity is starting at 0, so this basically cancels out and goes away. And so we have PF is equal to mg delta T. And then from our other principle, we have that momentum is equal to Bm. So we're just going to divide the momentum by m, and we get velocity is equal to g times delta t, and that will be the speed at the bottom of the swing. So part 2 of the question is asking you about the tension at the bottom of the swing. And so from the previous free body diagram that I drew before, we're going to have that the tension is going to equal to gravity. So we're just going to write this out as T1 is equal to mg. And we have m equal to 80 kilograms from our constants, and gravity is equal to 9.81. So we have T1 is equal to 80 times 9.81, and we get tension 1 equal to 784.8 kilograms meter per second squared, which is the same as Newton. Part 3 of the problem from web assigned, it's asking you for the speed and tension when the rope forms a 30-degree angle. So we have our person here chilling, screaming at the top of their head. And again, we're going to draw a free body diagram as well. So we have the tension from the rope coming here, right here, in our free body diagram. And again, the only other force is just gravity. So we have that. And then I drew the theta from the horizontal at 30 degrees. Find the sum of the forces in the x direction. And all we have based on our free body diagram is the x component of the tension of the rope. And so this we're just going to use cosine in order to figure it out. So we have T1 cosine of 30 degrees. So if you notice, we're going to end up as Fnet as a vector. So Fnet is going to be equal to So, since we have this formula already set up, we're just going to plug in the numbers that we already have. And we already have m equal to 80 and g equal to 9.81. We have this right here. And so, when we solve for T1, we eventually get that the tension is equal to 1568 newtons. And that is equal to your F net Y. Using the momentum principle as we did before, we're going to manipulate the final momentum to be V final. And so we do that by dividing the momentum by the mass, which gives you velocity. So since we divide this side by m, we're going to divide this side by m as well. So basically, the velocity at 30 degrees is going to be equal to Vf equal to F net delta T over m. Or it asks you to calculate the stretch of the rope while you're at the bottom of the swing. So again, the only force that is acting upon the person at this instant is gravity. So basically the force of the string is going to have to match the force of gravity. So we have mg is equal to the spring constant of the rope. And so in order to calculate the stretch, we have S, which is L minus L initial, and L initial was given before as 91.44. And so basically what we're going to do is we're going to move around like the variables just to solve for L. And so we have 784.8 newtons is equal to Ks negative L minus 91.44. And your L component in this case is just going to be 0, negative 1, just because it's just pointing directly down. And so just moving this around, in the end, we're just going to have divided by the spring constant, and it's equal to L minus 91.44 meters. So the stretch is just going to be equal to 784.8 divided by the spring constant plus 91.44 meters. Or we're going to set F net equal to the spring force again. So we have F net equal to that. So our overall formula is going to be F net divided by the spring constant times the unit vector of the force, and it's equal to the stretch minus the relaxed length of the rope. And so basically we're just going to have in the end F net over negative Ks times L hat plus L0 and it equals L. Similar to what we did on the paper, we're going to define the constants, gravity, mass of the ball, the relaxed length of the rope, and the spring constant of the rope as well. And using the same formulas that we used to calculate F net, we're going to also deconstruct it and find the parallel component and perpendicular component. And this is what the rope swing will look like. And you see how the first one is just looping back and forth, it is oscillating, and the F net and the F net perpendicular and parallel compensate for the F net.